Okay, so I have gotten a lot of feedback on this Unit 10 gases, and I think we just kind of need to do like a video so that I can try to explain the difference of this stuff to you. So the first part that we did, gases part 1, this was just on 4 basic laws. You have Boyle's law, Charles' law, Gay-Lussac's, and Avogadro's law. So this is kind of what leads us up to part 2. So the relationship of all of these laws lead us up into our ideal gas law. But the difference between that and this is that for this worksheet, you're really only comparing 2 variables at a time. And with the ideal gas law, you're comparing multiple variables. And also, in this one, you're going to have like an initial and a final. So for instance, let's go to number 1. So it says a sample of air has a volume of 140 mils at 67 degrees Celsius. So this is kind of like our initial condition. Okay, that's not a word. 1 second. Initial condition. So at what temperature, this is really what you're looking for. What temperature? And since we're just comparing 2 things, this can stay in Celsius. So we're looking for what degree Celsius would the volume be at 50 mils. So this right here is our final condition. So what's happening is we have a sample of air. Okay, and it is in this expandable, like I will think of it as a balloon or something. So it is in this balloon, and initially the balloon has a volume of 150 mils, and its temperature is 67 degrees Celsius, so it's a pretty hot balloon. So basically, what's happening is we're raising the temperature, and because you raise the temperature, the volume also has to increase, because as V increases, T also increases, okay? So what we're doing right now is it also says at constant pressure. So the only 2 things that we're comparing is V versus T right now, okay? So you go back up here and you say which one of these has only V and T. And you notice that that's Charles's law. So that means that our initial part is the 1. So that's V1 over T1. Let me use the correct colors. So that means that V1 over T1 comes from this initial part. And then the final part is your T2. So that means that we're solving, we have V2 over T2. And since we're looking for temperature, we're solving for T2. So what we do now is, since we know what we have and we know what equation we're working with, we're just going to solve for T2. Now, there's several ways that you can do this. You can go ahead and you can manipulate the equation, or you can just go ahead and put your numbers in. I always put my numbers in just because that's me, and I like to do that. So what I'm going to do is I'm going to fill in this right here. I'm going to do it over here. So our initial volume is 140 mils, and our initial temperature is 67 degrees Celsius. Okay, all I did was fill it in right there. And then our final, or our 2, so this was our 1 and this is our 2, our final volume is 50 mils. And all you have to do is make sure that mill and mill matches, like mill and mill, milliliter and milliliter. And then we're solving for T2. We don't know what T2 is. So there's several ways that you can do this math. I'm going to bring it down here so that you can see. You can go ahead and cross multiply if that makes sense to you. Not a big deal. And then we would get 140 mils times T2. And then we would get 50 mils times 67 degrees Celsius. And since we're trying to solve for T2, we want to divide both sides by 140 mils. So that would cancel here, and we're left with T2 equals 50 mils over times 67 degrees Celsius over 140 mils. So if you notice, this makes our units work as well. That's how you know that you did it right, because milliliters divides with milliliters and Celsius is left. So your math here would be 50 times 67 divided by 140, and I'll go ahead and put that in my calculator and give you an answer. Okay, so when I get that, I press the fraction bar, and I get that T2 is 23.9 degrees Celsius. And we want to make sure that that makes sense. So if volume increases as temperature increases, volume would also decrease as temperature decreased. So what happened is we went from, this is kind of a mess, I'm sorry. We went from 67 degrees Celsius to 23 degrees, or 23.9 degrees Celsius. So what happened to our temperature? Did it increase or decrease? Well, clearly it decreased. So we need to make sure that our volume also decreased. Well, our initial volume was 140 milliliters and our final volume was 50 milliliters. And that was a decrease in volume. So this is our answer and it makes sense, okay? So that's what we do here. I know this is a lot of mess, but I'm going to erase all of this and we'll do another one just so that we can get our bearing on all of this. If the algebra is your problem, then I will help you with that. I really want you to understand the concept, and I want to make sure that we understand the concept as well as the algebra and all that. So the second one says, the pressure exerted on a 240 ml sample of hydrogen gas at constant temperature is increased from 0.428 atmospheres to 0.724 atmospheres. What will the final volume of the sample be? So the first thing that we have to do is find our initial situation and our final situation. So our initial situation is, this one's kind of weird because it doesn't just straight tell you, but our initial situation says you have 240 ml sample of hydrogen. And the initial pressure is 0.428 atmospheres of pressure. And so then it says that we're going to change the pressure from 0.428 to 0.7424. And then it asks me, what is the final volume? So we're looking for the final volume. And the only two things that we have right now are volume and pressure. So again, we're going to go up here and we're going to see which one only deals with volume and pressure and temperature is constant. And that is Boyle's law. So we're just going to copy that down. I'm going to use my colors. I have P1 V1 equals P2 V2. Okay, so then you're just going to plug in your information and you're solving for V2. So I have my first pressure is 0.428 atmospheres. And my initial, I don't know why I wrote atom. My initial volume is 240 milliliters. Okay, and then I'm solving for V2. My P2 is 0.724 atm. And I'm solving for V2. So in this one, the math is just a little bit easier. I'm just going to rewrite it so you can see. I don't know why my pen is doing this. Okay. So since I'm solving for V2, I want to divide both sides by 724 atm to get rid of it to isolate that V2 over there. So that means that on this side it will cancel and we're just left with V2 equals 0.428, I don't know why it's doing this, times 240 milliliters. Again, that's over 0.724 atm. Make sure that your units work out. Since we're looking for volume, we want our pressure units to cancel, and they do. And we're left with milliliters, which is a unit of volume. So you put this in your calculator. You say on the numerator 0.428 times 240. And on the denominator, you put 0.724. And it gives you 142-ish milliliters, okay? And so again, we're just gonna check to make sure this makes sense. Pressure and volume are actually inversely related, so as one increases, the other one should decrease and vice versa. So in this one, our pressure is what does something. So our pressure went from 0.428 to 0.724, so our pressure increased. we want to make sure that our volume decreases. So our volume went from 240 milliliters to 142 milliliters. So our volume decreased, and that is our inverse relationship that we want. So that makes sense. So for all of these, all you do is just compare, you just find which one of these laws you're going to use and then plug it in. So the difference between these problems and our worksheet 2 problems are these always have some type of constant. So in this one you see you have a constant temperature, and the other one you see you have a constant pressure. There's always one of these variables that are constant. So if you go to your worksheet 2, it's not going to stay constant. So like for instance, number 3. Also, you don't have initial and a final. So this is something also that you're going to be dealing with the ideal gas law. So number 3, it says, how many liters does 0.8 moles of oxygen fill at STP? So there's not a lot of information there, very clear. So I'm just going to show you where this information came from. So for our ideal gas law, we have PV equals nRT. So we have 1, 2, 3, 4, 5 variables. So you're always going to be given 4 variables and solving for the 5th one. So we always know that R is a gas constant, and the constant that we use is 0.821 liters atmosphere over moles Kelvin. Okay, so that is always going to be your R. So you always have one variable already known. So in this problem, we're asked for how many liters. We're given that N is 0.8 moles. And then we have STP. What does STP mean? That is standard temperature and pressure. It was in your PowerPoint a few slides back, or maybe even in the part 1. Standard temperature and pressure is 273 degrees Kelvin and 1 atmosphere. So we know that our temperature is 273 K and our pressure is 1 atmosphere. So clearly the only thing that we don't know is this volume right here. So there are different ways that you can do this. You can plug in the numbers and then solve, or you can just manipulate the equation first. So PV equals nRT. We're solving for V. Let me color it a little different so that we can keep up with it. We're solving for V. So we need to get V by itself. So over here, P is multiplied by V. So to get rid of it, we're going to divide. And what we do to one side, we have to do to the other side. So then that means that P divided by P cancels. And we are given V equals nRT over P. So then you just literally plug all of these numbers over here. You plug them in. So I'm going to do that down here. So now we have V equals N, which is 0.8 moles. R, which is 0.821 liters atmosphere over mole Kelvin. Okay, T is 273 Kelvin, all over P, which is 1 atmosphere. So we're going to make sure that our units cancel out. So mole divided by mole is going to cancel. K divided by K will cancel, and atom divided by atom will cancel, and you're just left with liters. So when you put all this in your calculator, your fraction bar is going to look like the numerator will be 0.8 times 0.821 times 273, and the denominator will just be 1. So you put this in and you get 179 liters. That is the volume for this amount of moles of oxygen at STP. So the difference here is the previous worksheet we were working with like a comparison. So we're changing the scenario. Here we're not really changing the scenario. I'm just asking you, I have this amount of moles and it's at STP. So how many liters does it need? Okay. Alrighty, so let's look at number 5. So number 5 is partial pressure So the equation for partial pressure is back in your PowerPoint, and it's literally just a sum. So partial pressure is a sum of all the different pressures, okay, and so forth. So it tells me what is the partial pressure of a 1.2 liter container holding 1.34 atmospheres of water vapor and 0.83 atmospheres of oxygen. So really, all we do right here is I'm given this is like pressure A and this is pressure B. So all you really have to do is just add them up to get the total. So you have P of your water vapor and you have P of your oxygen. And so you're just going to add them up. 1.34 ATM plus 0.83 ATM. Add them together and you get, what, 2.17? Is that right? Hold on. 2.17. And that's your total pressure. That really is that easy. Some of these problems are not that easy because it may be like 1.3 atmospheres in 1 liter and 0.83 atmospheres in 2 liters, okay? If it gives you the liters here, that means that your pressure will change whenever you put it into a container of 1.2. But since it just says that this container contains this amount of pressure, you don't have to do all that. Okay, so let me erase some things so that we can do this last problem as well. Okay, so the last one says, what is the density of CH4 at 1.3 atmosphere and 20 degrees Celsius? So for this one, you need the other equation. If you go in your PowerPoint, which is where I'm going right now because I don't know this equation by heart. If you go in your PowerPoint and you look at the very last slide, it says density, okay? And it gives you an equation for density. It says that D, which is density, is equal to P, which is pressure. M, in this case, M is actually our molar mass. Okay. Wait, is it? Hold on. Yeah, M is our molar mass and all over RT, okay? So we have all the information we need. We know that P is 1.3 atmospheres. We know that T is 20 degrees Celsius, which, by the way, since we have R in this equation and R is 0.821 liters per atmosphere over mole per Kelvin. You see that Kelvin? If you ever see Kelvin in there, that means that you need to make sure your T is in Kelvin. So we'll have to change that 20 degrees to Kelvin. And M is molar mass. Well, we know that our substance is CH4, so we can find the molar mass of CH4. Okay, so let's find the molar mass real quick. So the molar mass, you just take C and you take H, and then you say how many of C? I have 1. How many of H? I have 4. The mass of carbon is 12, and the mass of hydrogen is 1. So that's 1 times 12 is 12, 4 times 1 is 4. You add them together, and you get 16. So that means that 16 is your molar mass and can go right here. Okay, the last thing we need to do is make sure that we transfer our, why does that keep doing that? That we transfer our temperature to Kelvin. So 20 degrees Celsius, the way you change it to Kelvin is you literally just add 273, okay? And you would get 293 Kelvin equals T. So now we just plug everything in and we say D equals P, which is 1.3 atmosphere, times M, which is 16 grams per mole, all over R, which is 0.821 liters per atmosphere over mole per Kelvin, times 293 Kelvin. Okay, so atmosphere cancels, mole cancels, K, and you're left with G over L. And density is a measurement of grams over liter, so that makes sense. It's a mass over volume. So in your calculator, your numerator is going to be 1.3 times 16, and your denominator is 0.821 times 293, and you get your density is 0.086 grams per liter. That's the density of CH4 at that pressure and temperature. All right, so I think that's everything. The other ones, you really can just use this information and plug in the values. So if you have any questions, just email me.